All right, I just wanted to make sure that actually the microphone was working. It is working. So now I am going to go over part 1C of question 1. Part 1B is very similar to 1A. Part 1C, only the first part of part 1C is different. The rest of it is similar to parts 1A and 1B. So I am going to go over only the first part, which is the reverse kind of reaction that we did here. So here we went from partial pressure in this equation. Let me show you. I don't know if you can see the mouse. Let me show you. So here in part 1B, we went from partial pressure, in part 1A, I'm so sorry, from partial pressure to mixing ratio. Now, in this part, we are going from mixing ratio, which is volume mixing ratio, to partial pressure. Okay, how to do that now? Again, we go back to the equation. So we've got this equation. Let me show you here. So P I, in this case, I is methane. So I is methane. So we've got Pi over Pt. It's a little slow. Vi over Vt. Okay, so volume mixing ratio and then partial pressures, partial pressure over the total pressure. All right, so we've got this value, which is the volume I over volume T, which is 1700 P, P, B, V, which means that it is volume over volume. Okay, but part per billion. What does that mean? It means that it is equal to 1700 parts of methane on top over 1 billion. I just use B. 1 billion parts of the, this is just slow, I don't know why. 1 billion parts of the total atmosphere. So 1700 parts over 1 billion parts. All right. But what we want at the very end is part over part, atmosphere over atmosphere. Now we're going backwards as compared to what we did in part 1A. We need to go backwards. Okay, how to do that? It's simple. So we are going to go from parts over 1 billion parts to parts over parts. So what we need to do is to convert this 1 billion parts just to parts. In order to do that, we multiply this by 10 to the 9, 10 to the 9, okay, divided by 10 to the 9, because we want to multiply the whole thing by 1. This ratio here is just 1, so we want to multiply the whole thing by 1, but in order to get rid of this 1 billion parts in the denominator and convert it to just one part, we have to multiply both the denominator and the numerator by 10 to the 9. Why is that? Why 10 to the 9? Because 1 billion parts is 10 to the 9 parts, right? 1 billion parts is 10 to the 9 parts. All right, okay, so I'm going to continue the calculations, but first converting that to parts. So how to do that? So this 1 billion and this 10 to the 9 cancel each other. And what we're left with is 1700. I don't know why my pen is going wild on me. So 1700, let me just quickly show you and then stop this video, make sure that actually this is working properly. So 1700 divided by 10 to the 9, 10 to the 9, part over part, which is atmosphere over atmosphere. And that's why here we did that. We divided by 10 to the 9. All right, part 1D is very similar to parts 1A, B, C, or similar to parts of those sections of question 1. So I'm not going to go over that. I'm going to move on to the next question, but let me know if you have any questions. Calculate the densities of the following gases at 25 degrees Celsius and 1 atmosphere. This is question 2. We've got different species of different molecules here, and we're going to calculate the densities for all these molecules, assuming that the pressure and temperature are the same for all these gaseous systems. All right, so temperature is 25 degrees Celsius. We need to convert it to Kelvin. Why is that? I'll explain it in a second. Pressure is 1 atmosphere. In order to calculate density from or based on temperature and pressure, there is a very useful equation that we can use. It's the ideal gas law, PV equals nRT. And then what is density? Density is here, mass over volume. We already know it. We can rearrange this and manipulate this equation a little bit and make it into a form that gives us the equation for pressure versus, for example, density. Okay, so how to do that? So look, if I rearrange this equation. So this is N over V, which is C, but we're not going to really talk about C. So N over V, so if you divide both sides, N over V multiplied by RT. But now we don't need the number of moles, we need mass. We want mass over volume, because then we can replace it by density. Okay, how to do that? We can use the relationship between the number of moles and mass. The number of moles multiplied by molecular mass, which we show it by capital M here. It's going to give us the mass. Therefore, we've got the number of moles in this equation, right? So how to get the number of mass? So it is equal to, now, instead of N, I'm going to use mass over M divided by V, RT. Okay, so it is equal to mass over V divided by M as well at the same time. So let me do it this way. M R T. This mass over M over V is density. So it is equal to rho over M R T. Okay, rho over M R T. So that's really what we need here. Okay, so now how to calculate rho? Rearrange this equation. So P is now equal to rho over M multiplied by RT. So this equation is exactly that, but we need to rearrange it. So rho is now equal to MP, this is P, MP over RT. If you rearrange this equation, right? And this equation is exactly the equation that is used here. All right, great. So we showed that. Let me know if you have any questions about this part. But now, what we need to do is to calculate the density. The question wants us to calculate it in grams per liter. Grams per liter. How to do that? Okay. Let me erase these. All right. So we've got all these values. We've got the pressure, we've got the molar mass of, for example, nitrogen, if we start with nitrogen. And then we also have a value for R in the equation sheet, or two different values. Which one should be used? It depends on the units that we're using. And then temperature is always in Kelvin, right? We're using the ideal gas law. So what is the pressure? It says 1 atmosphere. So we're going to use that 1 atmosphere. So plug that value into the equation. And then what is the molar mass of nitrogen? It's either given or we ask you to calculate it. Usually it is given. Okay, usually it is given. But if it's not given, so as an atmospheric chemist or scientist, we need to be able to calculate it. Here is the periodic table, if I can access it. This is the periodic table that will be given in the exam. So what I want you, for example, for carbon, use only 1 decimal place. Okay, I can't show you here probably. So 1 decimal place. So 12.0 for carbon. For nitrogen, 14.0, only 1 decimal. If you need to round it up, you need to do that. Please do that. Okay. So for example, for hydrogen, it is 1.0. For neon, it is 20.2, right? 20.2, because you have to round it up because the next digit is 7. So we learned this in first year chemistry. All right. Okay. So mass, let's say the molar mass is given, it's here, or you calculated. Don't worry about 2 decimals here. You're just going to use only 1 decimal. And then, so you've got the mass, which is in grams per mole. This is important. We wanted the density to be in grams per liter. So it is already in grams, which is great. What about moles? We need to get rid of this moles, number of moles, because at the very end, what we want is grams per liter. Okay, we have this R, the gas constant, which is in 2 different values that are given in the equation sheet. Which one to use? Liter atmosphere. So we need the liters, and atmosphere already is given. So pressure is in the atmosphere. So it's better to use this value, because at the very end, we want liters, the volume, to be in liters, and then the pressure is already in atmospheres. So atmospheres and atmospheres cancel. Mole, inverse mole and inverse mole also cancel each other. Kelvin and inverse Kelvin, they cancel each other. So multiply all these values together and divide them by, so these 2 values on top, multiply them, divide them by these values. You should get this. And then again, if I show you, Kelvin cancels Kelvin, mole cancels mole, atmosphere cancels atmosphere. Look, what we're left is is gram per mole for the density. And the rest of the question is very similar to this part. Let me know if you have any questions. All right, in the first series, this question is the last question in part 1 of the first series. This question is the last question. We talked about root mean square velocity in our last lecture. Please watch the video. Let me know if you have any questions. We are going to calculate the average velocities of these gases at 25 degrees Celsius. Look, according to this equation, we only need the temperature to calculate root mean square velocity. That is one thing. So we need temperature. Of course, we also need the molecular mass of those species that we are calculating the average velocity for. The other thing is that R is a constant. 3, of course, is a number there. So we need temperature. The temperature should be in Kelvin. So in this equation, the temperature should be in Kelvin. And molar mass, of course, it is always in gram per mole, but we need to convert it because of the requirements of this equation and because of the unit that we need for the velocity at the very end, which is usually in meters per second. Look, the unit is meters in meters per second. So when we work with these values, we want to make sure that they are in the right unit. Okay, that's one important thing that actually I needed to mention. But there is another important point here as well, that in the exam, I may not give you this question, this equation in the question. So this equation may not be given in the question, but in the equation sheet. This is tentative equation sheet. So I will give that equation in the equation sheet. All you need to do is to recognize it. So make sure that you recognize this equation is for root mean square velocity. Usually the root mean square velocity is used as a measure of the average velocities or average velocity of the particles in the system, usually. But sometimes I might use the most probable velocity. So go back to the notes. There is another equation as well. So I might ask you in the exam, I may ask you to use that. And then the equation is given, both of them, the root mean square velocity and the most probable velocity. Both of them are in the slides in the last lecture that we talked about on September 7th, September 7th. So both of them are going to be in the equation sheet. You need to recognize them and use them. So this is the equation for root mean square velocity. We're going to use it. We just talked about the temperature that should be in Kelvin. The other thing that is important is also this R. So for the gas constant, we have two different values with two different units. Which one should be used? We are going to use joules per mole Kelvin. Kelvin. Why is that? Okay, so if we use this value into this equation, look, we've got 8.314 joules per mole Kelvin. The temperature is already in Kelvin, so Kelvin and Kelvin will cancel each other. So these two cancel out. Now, the next question is, okay, so how to cancel? At the very end, we want meters per second. But now, how to cancel this gram per mole that is in the denominator? Assume this is gram per mole. Assume that it is gram per mole. In the denominator, how to cancel it with joules? We have to first figure out what is in 1 joules. 1 joules is a group of units together. Okay, so what are those units? Look, it's in the equation sheet. It's given. 1 joules is 1 kilograms. Sorry, this is, I will fix this. This is meter squared. It's not inverse meter squared. Meter squared, I will fix this. Meter squared over second squared. So that's 1 joules. Now, so we are converting this. If we use this conversion factor, we're converting these joules to the units that are now useful for us, and we can use them as the unit of the velocity. So look, now we've got kilograms meters squared over second squared, and by using this conversion factor, we got rid of this joules. Now we don't have joules anymore. All right, but for the velocity at the very end, we need meters per squared, sorry, meters per second. In the square root, we need that meters squared over second squared in the square root. But we don't need this kilograms. In the denominator, we have gram per mole. So it's better just to convert this gram per mole to kilograms per mole. And that's exactly what we did here. Look, by converting that, we get rid of that grams, and now we have it in kilograms. Kilograms and kilograms cancel each other, and then mole, of course, here cancels this mole. So what you're left with is meters squared over second squared. So it is required actually to do these conversions inside the square root, and at the very end, we get this unit inside the square root, which is meters squared over second squared. If you take the square root of that unit, is going to give you meters per second. So we're good now. Now we can start just multiplying these numbers together and dividing them by this value. Please do the calculation for this. Make sure that this value is correct, and let me know if you have any questions. So this is the end of tutorial 1, which I covered the questions in Dr. Perry's worked examples, series 1, part 1.